Welcome to lecture 7. In this lecture we will see some elementary concept of electrical motors and generators which will be useful for our further studies. Now this is a diagram of a motor where this is the north pole and this is the south pole, and this is the rotating part shown in red color, and this is the conductor in the rotating part or the rotor conductors. The cross indicates that the current is entering the conductor like this, and the dot indicates that the current is coming out of this conductor like this. Actually the conductor is placed in this way, perpendicular to the plane of the paper. So the force that is experienced here can be obtained, the direction of this force can be obtained using Fleming left hand rule. If you apply Fleming left hand rule, then the first finger gives the direction of the field, this finger, second finger, gives you the direction of current, and the thumb gives you the direction of force. So the force is in this direction. If you come here, the direction of field remains same, but the direction of current reverses. So here the direction of force is in this direction. So the direction of force here is in this direction, and the direction of force here is in this direction. So what is the magnitude of this force? From your class 12, you know that this force is equal to B into I into L into sine of theta. Now these conductors are always placed perpendicular to these lines of force, so sine theta will be 1 here. Now what is the torque? The torque is equal to B I L into this radius R. Now there are two such forces, one acting in this direction, another acting in this direction. So the total torque produced by both the conductor is equal to 2 into B I L into R. Now instead of one conductor, if there are n number of conductors, then torque total for n number of conductors will be equal to this into n. Now to express it in a different way, we can write this B as flux by area. What is B? B is flux density, so I have written it as flux by area into I into L into R into N. Now this can be written as 2 into L into R into N divided by A into phi into I. Now what I have done, these parameters, 2 is a constant number, L is the length of the machine, so once you make the machine, this number is constant. This R is the radius of the rotor, once you make the machine, this is constant. This N is the number of turns in the rotor, and once you make the machine, again this is constant. A is the area, this area, once you make the machine, this is constant. So these parameters are constant for a machine. From machine to machine it will vary, but for a particular machine this is constant. So we can write it as K into phi into I. This is the torque produced by the conductor, or by it produced in the rotor. Now this result is useful and it will help us in answering many questions when we will when only thing that we need to understand is that the torque is proportional to flux as well as current. If we increase the current in the rotor, then also torque will increase. If we increase this flux in the machine, then also the torque will increase. So this is applicable for all machine. It is not that this is only for DC machine. It is applicable for all machine. Only difference is that how the flux and current is derived. Now this is about motor. Let's look at a generator. If you look at a generator, we know something. Let's revise this once again. We know Faraday's law of electromagnetic induction, which says that if we have a coil like this, then the EMF can be induced in this coil if the flux linkage with the conductor changes, and the magnitude of the induced EMF is proportional. Magnitude of induced EMF is proportional to the rate of change of flux. And one more thing, the induced EMF is such that it opposes the cause for which it is induced. So we can write it like this, minus d psi by dt. What is psi? Psi is the flux linkage. Now, what does Faraday's law state? It states that whenever there is a change of flux linkage, EMF is induced. And the magnitude of induced EMF is such that it opposes the cause for which it is induced. And the direction is such that it opposes the cause for which it is induced. The magnitude is proportional to rate of change and the direction is it opposes the cause. The last one is also known as the Lenz's law. Now let's look at these statements. Now I have taken it from Wikipedia. You can also have a look. Generating an EMF through variation of magnetic flux through the surface of a wire loop can be achieved in several ways. Let's first understand what is meant by surface of a wire loop. So if you make a wire in a loop like this, then this is the surface of the loop. Now here it is said that generating an EMF through variation of the magnetic flux through the surface of the wire loop. That is, if we vary the surface area of this loop, then also EMF will be induced. Now how you can change that? The flux can be changed, that is the magnetic field B can change. This happens in a transformer. Wire loop can be deformed, that is you make a loop and change the shape of the loop. Where it is done in strain gauge. Orientation of the surface area changes. This happens in a generator and any combination of the above. Let's look point number 3 in little bit more detail. Let us consider that this is one pole of a machine. This book is one pole of a machine and this book is another pole of the machine. Now these pages can be thought as the lines of force coming out of this pole, and this conductor and this scale can be thought as a wire loop. That is, this scale is making a loop. On this side you have a conductor, it makes a closed path through the periphery of this conductor. So this is called a wire loop. Now if you place this conductor here like this, then the lines of force are parallel to the area formed by the loop. What is the area formed by the loop here? It is the area of the scale. If you place the scale like this, then the area of the scale is parallel to this. Now, and if you place it like this, the area of the scale is perpendicular to the lines of force. Now, let's see if it is like this, how many lines of force are passing through this area? It is 0 because this area is perpendicular to the lines of force. If you place it like this, the whole flux is passing through this. If you make an angle like this, then which area is perpendicular to the lines of force? It is this vertical line. This vertical from the paper to the top of the scale is the area that is perpendicular to the lines of force. And if you make a triangle out of this, you will find that this is nothing but the sine of theta, where theta is the angle formed by the scale to the paper. Let me repeat this. What I am saying is that the area through which the flux lines are flowing is this area, which is the perpendicular distance from the page to the scale, this area. Now what is this area? This is if this area of the scale is A, then this area is A sine of theta. Now at this point the flux linkage or the flux passing through the scale is 0, and at this point the flux passing through the scale is maximum, and at this point it is this area into sine of theta. Now let's look at this diagram here. Now this position is represented like this. When I put the scale like this is represented by this line. So here the flux linkage is maximum. The most of the flux is passing through this scale. Now when you come here, the scale is in this position, and hence the flux linkage is minimum. Again when I come here, the scale, initially it was like this, then here it is like this, here it is like this, here again it is maximum, here again it is like this, and finally at this point it is like this. So I can see that the flux linkage or the flux passing through this scale is maximum, 0, again maximum in the opposite direction, again 0, again maximum. So it is varying. As I move the scale, the flux linkage with this conductor varies. And we have also seen that this area is a sinusoidal function. So what we get out of this? We get out of this that the flux linkage with this conductor is a sinusoidal function. What is flux linkage? Let me repeat this. What is flux linkage? If I have two poles like this, flux lines are coming out from this pole. Say if this is north pole, this is south pole, flux lines are coming out of north pole and going into the south pole. Now if I place a conductor here, then the number of flux of lines of force that is passing through the area that is perpendicular to this lines of force is the flux linkage. Now if I place the area like this, then none of the flux lines are passing through it. If I place it like this, all the flux lines are passing through this, and if I place it like this, the number of flux line that is passing through this is sine this area into sine of this angle, that is this area from this point to this point. So I can write this flux linkage psi, the flux linkage psi as psi max, that is the maximum flux linkage, into, it's a sinusoidal function. I can write it as sine theta or cos theta. The way I have drawn this is a cos theta into cos of theta. Okay. Now what is induced EMF E? E is equal to minus d psi by dt. Now what is d psi dt here? It is minus d dt of cos, I can write theta as omega t. So what is cos omega t? What is the derivative of cos omega t? Derivative of cos omega t is sine omega t into omega. So we can write it as omega sine omega t. So if I have a cosinusoidal function as a flux linkage, my induced EMF will be a sinusoidal function like this. So this will be a very useful relation that we will use throughout our study. What I want to say is that the flux linkage is leading the induced EMF by 90 degree. That is, if the flux linkage is a cos function, the induced EMF will be a sine function. Now let's try to correlate this with this diagram. This diagram is available in almost all books. Let's try to relate what we have studied between this diagram and this diagram. Now, when we have drawn this diagram, we have assumed that the poles are like this and the conductors are moving in this way. Now, in paper, you really cannot draw a movement in 3D. So, a movement in this direction like this is drawn here as a movement like this here. So, this circular movement here is represented as a circular movement in 3D. So, when these conductors are parallel to these lines of force, we show the conductors to be here. So what is the flux linkage at this point? Since the conductors are parallel to the lines of force, the flux linkage will be minimum here, that is somewhere at this point. So the induced EMF will be maximum at this point. Now if I come to this point, this represent placing the coil like this. So here the flux linkage will be maximum, say at this point, and the induced EMF here will be minimum. So if I place the conductor here, the induced EMF will be minimum. If I place the conductor here, the induced EMF will be maximum. So we will see one more class on elementary operation of a motor and a generator, and then we will go into synchronous machine. So what is required from this class is this relation, that is relation between induced EMF and flux. Thank you.